Introducing Portraits and Ideas. I'm Erlen Nisgal presenting interviews to inspire and perhaps unveil something new in the realm of ideas. Today on our program, we would like to introduce Professor Suk-Ho Chung, who is a professor in mechanical engineering at King Abdullah University of Science and Technology. What is your professional position in KAUS?
I'm a director of the Clean Combustion Research Center in KAUS.
And what is clean combustion?
Clean combustion, the combustion generates a lot of pollutants such as NOx, SOx, and soot. And clean combustion is to reduce those kind of emission. Simultaneously, recently we have problems of CO2 that leads to the climate change and global warming. So how to efficiently burn fuels for energy conservation.
So your area is extremely important for the world in terms of advancing the, how should we say, the consumption of fossil fuels. Is that correct?
Yes,
Yeah.
Consumption of fossil fuels and for the sustainability in the future.
Right. Why did you decide to come to KAUS?
Well, I see there is a lot of opportunity. I can work with many prominent scholars over here, and also in the combustion field area, I can work on many eminent people work together on various aspects, like experimental approach and computational approach, and so on. So I decided to move to KAUS.
Also, there is the potential of linking up with the group that are doing the similar research at Aramco, potentially.
Oh yes,
Yeah.
Aramco is one of the largest world oil producers and also natural gases. So I see there is a lot of potential to collaborate with Aramco people, and especially the combustion research on the perspective of and for the benefit of the kingdom.
Amazing. What advice would you give to the youth in Saudi Arabia to promote their interest in pursuing science careers?
Well, science is a quite general question. It's a very interesting subject first, and it is very diverse. As I recall in my early career, maybe I can explain some of the things during starting from my high school years. In the high school years I hated chemistry. So I decided to go to engineering college, and I decided mechanical engineering. And then I hope I never will get involved in the chemistry area again. But as time goes on, I have selected the combustion as a major subject. And until during my PhD work, there was no problem about working on combustion without knowing any chemistry. And then the things has been changed in 1980s, and then the emission issues came in. So in studying combustion, we need chemistry to understand and predict the production of those emission pollutants. So I started study on chemistry after the graduation of PhD. And along with that, in 1990s, the laser diagnostics capability came into combustion area, so we can see a lot of things that could not be seen previously. So and for that, a lot of optics, physics, and spectroscopy, those new science I should learn it. So science is a continuous learning process, and it's very important for the adaptability for one to be involved in science, because it's getting deeper and deeper, and it's getting more interdisciplinary and multidisciplinary. In that aspect, there's always a new information you will need to learn. One needs to learn, and it's a very fun area to study.
I think a lot of the students will resonate with the idea that it's fun. That would be a very attractive for them. Did you wake up every day going to work and you're looking forward to the challenge for that day and the fun that you'll have in the lab?
Yes, especially experiments or computation, we could see a lot of new things, new phenomena, and try to analyze new things. So it's always encounter new things. That is similar to having a tour, sightseeing tour. Every day we may encounter new things, new information, new environment. So it's a fun area.
That's a great example to say that working in your field in science is like a sightseeing tour. That's a good way to reference that. You mentioned that you had a tough time with chemistry in the beginning, and then you revisited years later, as well as several other fields like optics and so on, and lasers. How did you find it the second time around? By the time you had gotten your PhD, was it a lot easier for you?
No, it was a lot more difficult. So sometimes I regret that I should study harder during undergraduate or even high school to broaden my discipline.
Right.
But after that, the learning process is much more difficult, much more slow. But I go through with the help from others, a lot of discussions, having consultation from others, and so on.
So that's actually good advice for youth who might run into difficulties in a subject, to go get advice from others, right?
Sure.
Find out who knows and let them give you some tips about it.
Yes, that's right. One key to that area is very important, and you can get it easily from others who know that area well.
That's right. Yeah. Actually, I have a couple of questions about this a little bit later on. But you actually started the next question, which is how did you reach the position you're in today in your profession? Let's just go through the milestones of your education and see how you advanced to the PhD, and then how you made decisions on your career track after the PhD. This will be interesting just for students to hear how you got to where you are now.
Okay, I studied, I graduated university from Korea, and at that time the graduate level education in Korea was not well established in late 70s. So I decided to go to US. And so I had my master's and PhD degree at Northwestern University in US. And then I came back to Korea as an assistant professor at Seoul National University. And since then I stayed there over 25 years. And this is another chance for me to move to coast, to change my career, to broaden up, and to see more chances to work with others. During the stay in Korea, since it's a small country, I have been involved in many different type of project that is related to combustion. So during that period, I think it's
a fertile period for you and the possibilities. I understand from previous conversation with you that you actually set up your lab in the beginning, and you were one of the first to do this kind of research in Korea.
Yes.
And so that must have been quite a challenge for you, to assemble your team and to get the funding and to get the support that you would need, as well as to actually put that lab together.
Yes.
What was that like?
Well, for this laser diagnostics tools are using very high power lasers, and those equipments were very expensive those days and even now. So for a system, to make one system, it takes several years to buy one piece, one piece.
Of equipment.
Of equipment.
Right, right.
So sometimes it's fun. First year, for example, I bought the ND-YAG laser. It's a very
YAG laser, right?
YAG
ND-YAG laser,
yeah,
right.
yeah. And then I thought, what I'm going to do with this YAG laser alone. Other equipments, it'll take 3-4 years to complete one setup for laser system. So I thought, well, laser, I can use it for laser ignition source. So first I got involved with the laser and I worked on the laser ignition system, and then we have some ideas to put in, and we could achieve multi-point ignition with a single shot laser at that time. So it was fun, you know. So it's kind of, it's adaptability.
Mm-hmm. Has that technology been put in automobiles? Yeah.
Not yet. I have a patent, but it will take some time.
Right, right.
Still, people are working on in UK and US.
Perfecting that.
Yeah, perfecting that and to apply for large size internal combustion.
How does that work? I mean, explain it in simple terms. What a laser ignition system is.
Laser ignition is if you focus the laser, then a lot of energy is put in one point. So that is called laser induced spark ignition. So many people has already been working on that subject.
Mm-hmm.
But if we focus the laser, not all the laser was absorbed. There is a remainder of the laser energy. So we thought how to utilize those remainder of the energy from the laser after spark ignition. So we had an idea about some cavity. So we guide the laser beam into the cavity and the cylindrical cavity. So we could effectively focus the laser beam along inside the cavity center line. So then we could have a secondary ignition source. So in that case, with just one laser, we could achieve multiple point ignition that could reduce the combustion time in engines and could increase the efficiency.
So that would increase efficiency, save fuel, and so on.
Yes.
So that they're tremendous. If you imagine all the cars out there using something like that, the total amount saved and energy and efficiency created would be quite significant. Yeah?
It could be, but still the system is using laser system is quite expensive.
Right.
So these days people are thinking about applying laser ignition system to gas turbines or special purpose internal combustion engines.
Right, right. So what are the milestones? Like for example, you decided at some point to pursue and get a PhD. What made you make that decision? Did you get good advice, or did you have sort of your own compass told you this was a good idea?
Well, it's the idea maybe it triggers in say 1969 when Neil Armstrong landed on the moon, and that was the time that TV was introduced in Korea relatively widely, so we could watch the launching of the Apollo and also landing and so on. So the launching of a rocket was amazed me at that time, and so I thought maybe I will do some propulsion type of research, and then I enrolled in the university after graduation and moved to US, and I had a chance to work on combustion.
That's interesting that you had a stimulus from the space program to go into this area, and then you choose Northwestern University in the U.S. So from early on, you had your mind set on getting a PhD, even before you got to university, so to speak.
Oh yes.
Uh-huh.
Yes.
So
in Korea at that time, is the goal of education was very high in many of the families and many of the students at that time. And it's a great change period of Korea during 1960s and 70s.
Tell us about that just briefly. I mean, obviously, you know, being immersed in an environment like that is a big advantage in a sense, because you get all this motivation from society to go into some challenging career and to take a challenging course in school. What was that like? I mean, when you were even in high school and in middle school, they were talking about the importance of getting a high level of education in your family as well as in school.
Oh yes, it is. Well, it's a Korean history. It's always the education was the best priority in the society. And after Korean War in 1950s, we were very poor at that time, and we had the motivation to improve the society through education. And especially in Korea, we don't have any resources, natural resources, and too many people.
Right.
And so
a lot of challenges.
Yeah.
A lot of challenges.
The only way is through education.
And Korea is a remarkable example of that, because, you know, as you said, in the early 50s after the war, you know, Korea was a very undeveloped country.
Yes.
And now it is certainly in the developed world and has, as I understand, one of the most high-tech societies around. And so you can attribute most of that, or if not all of that, to the educational advances that took place in Korea. And that history, if you will, the cultural history that goes back many centuries about the importance of education.
Oh yes.
Yeah.
Yes. In old days, there is saying that many of the college students pay their fees by selling cows. At that time, cow is a very important animal for agriculture in the society.
Right.
So even the families in rural areas, they even sell cows
To get their kids educated,
to
get their children educated.
Yes.
So that would be like selling camels in Saudi Arabia.
Oh yeah.
Right, exactly. What would you consider the relative advantage of hard work versus high intelligence in getting successful or being successful in your field of study?
Well, always hard work is most important. It's more important than high intelligence. Well, it's a very slow process of doing research is a very slow process. So you must put a lot of efforts on it. Sometimes one might need some bright ideas, but in most cases it's hard work and very steady type of work is required. Think it over and over and over again, rather than some blink of ideas.
So actually, by suggesting the importance of hard work, that would give a student out here who might perceive themselves as being not necessarily the smartest in the class, that would give them a lot of hope, right? That they could actually pursue it with the idea of working hard and closing the gap with that person next to them who might be thought of as a bit smarter.
Yes.
Yeah.
Through this working hard, you come up with a lot of, let's say, instances that can provide you ideas. By having a lot of experience, you can have those ideas. So through this very steady work,
Right.
Slow and steady is
the way to go.
Is the way to go.
And also, we can talk a little bit about failure. Failure doesn't necessarily mean a bad thing, because you can get new ideas through your failures. And I'm sure in your line of work, where you're doing a lot of different experiments, that failure is a part of the game, so to speak.
Sure.
Yeah.
Yeah, I used to tell my master students that it takes 2 years in Korea to get a master's, 1 year for coursework and 1 year for thesis work.
Right.
And if one is doing experiment or even numerical work, I always tell the students that in your thesis, if you repeat it in the final stage, you can do it in 1 week. And so the rest of the almost 2 years is the repetition and also failure.
That's right.
Yeah, a lot of things you fix it and fix it and fix it,
Right.
and finally you get the data that is meaningful.
Right.
So if one wants to repeat his work, then he can repeat it. Once you know it, repeat it it will take 1 week. But the other 2 years is all this,
Trial and error.
Yeah, trial, error, and
Right.
improvement.
Repetition.
Right. Not necessarily repetition, but improvement.
Improvement.
Yes,
Improvement.
yes.
Right. Right.
To get to the right set of data that is meaningful.
Well, I think that's important for a student, especially a young student, to realize that the frustrations that might occur when things don't go right and you run into stone walls with understanding and experiments don't succeed, that in fact that's all a part of the process.
Oh, yes.
And
yes.
at the end of the day, you say what they took 2 years to do, they could actually do it in 1 week once they get good at it.
Oh,
you know?
sure.
Yeah.
Sure, yeah.
So that's very good, encouraging words for a student. When exactly, and you already answered this to a certain extent, did you decide to become a scientist researcher? You pointed back to 1969 at the moon launch of Apollo 11. Was there any time prior to that, or any time after that that you thought was a turning point?
Yeah, in 1960s there was a competition between U.S. and Russia on the rocket program, and
Yes.
Soyuz and all
That's right.
kind of programs. So we were familiar with. I was familiar with that.
You followed that very closely.
Yeah, very closely.
Yes,
yeah.
yes.
And at that time, the science and engineering was a very popular subject in Korea at that time for many students.
So, okay, give me an example now. If you have a class of, say, 30 students, how many would be interested in science and technology careers in Korea? Let's say in middle school.
At that time, about 2/3.
Really?
Science and engineering.
66%.
Yes.
That's quite a large number.
Yes.
And
We have 12 classes, and 8 of them were in science and engineering.
8 out of 12 courses in your school.
12 classes.
Yes.
Yeah, classroom. Yeah.
Classrooms.
Yeah.
Right. So that's a large proportion of courses as well. I mean, that were devoted to science. So obviously your educating system and the educators in Korea, they were pretty aware of that importance, and they made your system, divert itself to that. So as a result, now when you got in college, when you got in university, were those proportions the same? You had a high proportion that was studying science and technology when you did your bachelor's?
Oh yes, we spent say 1 year for general education, like literature, psychology, and politics, English, and so on. But the rest of the 3 years we spend all the time for.
Not the entire student population. I mean, that was your department. But what about the huh?
Yeah, my department.
So what about the whole university? Okay, your university is pretty large. What is it, 30,000 students or something like that?
Yes.
So what proportion of those would be doing science and technology?
Oh, I think about 60%.
Really?
Yeah.
The same similar percentage as you talked about in
Yes, including medical school.
Yes.
Science, engineering.
That's a very high percentage. I would imagine you'd have to go to quite a few countries before you would find that level of percentage that would be studying.
Well, engineering school itself is about 30%. So all science and engineering together about I think about 60%.
So now let's go back before '69 when you were, say very small. Was there any stimulus from any other things about science and technology? Or your parents, were they inclined to coach you to do this, or your friends when you were playing with your friends growing up? Were you talking about this at that time?
Oh yes, I have an uncle who was majored in aeronautical engineering. I had also a lot of stimulus from him.
So that was a motivation. That was a kind of inspiration for you. Say, well,
Yes.
hey, my uncle can do it, and he probably talked to you a bit about it,
Yes.
about going into.
Yes.
Do you have any brothers and sisters that also decided to go into science and technology?
My younger brother
Mm.
in engineering.
In engineering as well.
Yes.
What scientists in your youth inspired you the most, and why?
Scientists?
Yes. You know, like if you were reading about science and you saw this particular accomplishment by a scientist, what was there any one or two that really you remember stimulating your interest?
Well, it's certainly the Einstein is a very good example,
Right.
and very unique scientist.
Right.
And not everyone can be like Einstein. It's
Sure,
a brilliant idea here.
Yes.
It's a totally new approach.
Right. He worked in the patent office, and
Yes,
in his spare time, he wrote some of the most important papers of the 20th century.
Yes.
That's right,
Yeah.
on relativity.
Yes. But others, there is a learning process.
Mhm.
It's somewhat very slow
Mhm.
process. Little by little, we gain information, and suddenly there is a jump
Mhm.
in the understanding.
Were there any Korean scientists that were like national heroes at the time that you knew about?
Yes, at that time, it's in agricultural areas.
Mhm. They were increasing the crop yields for rice or something like
Yes,
that?
yes,
Uh-huh.
yeah.
These were the major advances that they accomplished.
Yes.
How much time did you spend daily studying and learning that and the skills, to get the skills that you would need to be successful in school?
Mhm.
And what were those skills? What were the key skills to be successful as a student?
Well, there is some statistics that how much time we are spending in each areas in engineering school. So after graduation. So after graduation, the statistics shows you spend about 1/3 of the time on engineering, and equally 1/3 of time for documentation, and 1/3 of the time for meetings and communication. So communication and documentation skill is also very, very important to present your ideas and to persuade others and so on. So I think in the high school years or in undergraduate level, this communication and documentation, writing skills is very important. And also some of the leadership is important, but that is somewhat, I think, is somewhat difficult to learn. But you should work with others in many projects together.
Right. You know, the general impression about a scientist is that they are kind of they are over in the lab. You know, they don't really interact with people a lot, and they don't necessarily communicate a lot. That's the kind of reputation they have. But you are bringing out a point that's, I guess, very important. Is that communication skills are very important, because if you have a new idea, if you can't communicate it to your colleagues and to the rest of the world, then that idea may not take hold, and nobody else may find out about it. You know, so you got to learn how to write it up.
Yes.
You got to put it in a peer-reviewed paper, and you have to be able to communicate it verbally to your colleagues, and so on. So that's a very important point, I think you're mentioning now.
Yeah, and that's the statistics for the company. But even in university, we need to communicate with the student, with professors, and among the faculty members, and among the colleagues in the same areas. So communication is, I believe, is very important. And that part, I still need to polish a lot.
Well, you're doing a great job right now. Here's the other question. Now, going back to the skills, like when you were like in middle school and you were looking at studying after your classes, when you got home, how many hours would you put in every day? Just to do your homework and then maybe do some extra work.
Well, it depending on the year. So we had the entrance exam for middle school and entrance exam, national entrance exam for college.
Mm-hmm.
So in the later part of the years, just before the entrance exam, we spend almost our time for study.
Preparing for the exam.
Yeah.
That would be 4 or 5 hours a day after regular school?
I think more.
Really? More?
Yes.
So that's taking you to like 10 or 11 o'clock at night, right?
Oh yes.
Thereabouts.
Yes.
And that's even before university.
Before
So
university.
after university, it got to be after midnight. So
Well, after university, many students get tired of those lives. So first, second year, they somewhat relaxed, and then in many cases, then one face a problem in the senior years.
they already sort of passed the big hurdle to get in.
Yeah.
So then they kind of sort of lighten up a little bit. But nevertheless, I mean, obviously the teachers in the university knew that you all were pretty good students to get accepted.
Mhm.
So they probably challenged you pretty severely with the
Yes.
amount of work you had to have done, right?
Yeah, because of this education system, it was very competitive until get into university. But as I recall now, then actual starting of the study is from the university.
Oh, okay. That's when you really got serious, so to speak.
Yes.
And then it became perhaps more cooperative among the students at that point?
Yes.
Yeah.
We have a study group and
Right.
study together.
Right.
And if one could solve the problem, then teach to others. And,
Right. Now here you have a lot of students out here who are facing this question about exams.
Mhm.
What are your tips on students preparing for exams based on your experience? Now we got to go back a few years for you to think about that, but you know, obviously you were successful and you were able to leave career at an early time to go to the U.S. That means that you were highly accomplished to be able to do that. How did you prepare for your exams? What was your strategy?
Well, strategy is difficult, somewhat difficult, but well, I want to emphasize on math and science. I think a slow understanding is the key, I think, for the success. Because if you disappoint your achievement too early, then it's a very bad aspect. One can learn it very slowly, and understanding is mathematically is called some asymptote or something like that. It goes up very rapidly, then it approaches at certain level. And if
Tapering off, yeah.
tapering off.
Right.
So if you go up to the hill, you cannot see it very far. But if you go a certain level, then you can suddenly see the horizon or something like that.
Yeah, that's a good analogy.
Yeah,
I like that.
So until you go up, you don't know where you are. But it's maybe I can put it this way: it's like climbing up a mountain.
Yeah.
Until you go up, you are surrounded by trees, so you don't know where you are. But once you are very near the top, then you can see a lot of things. So I think a learning process is something like that. It takes time until you reach a certain level. Then suddenly the worlds, the things are getting brighter.
So you have to keep climbing on faith, so to speak,
Sure.
that you will reach the top and you'll be able to see off into the distance, which carries you to new areas and so on. So, like for example, in your preparation for exams, did you sit down and work a lot of problems as practice and spent those hours that you talked about that you spent, which carried you late into the night? What would you be doing? I mean, you just be reading a book, or you're working out problems. How would you go about, the actual details of the study?
In high school?
And before you got into university, and even after you got into university, you obviously had a system that you developed.
There were many good books and reference books. For example, in math, we practice various problems, and then math is a thinking process, so one needs to train them. You cannot solve it at once. So.
Would you consider math a key course that a student needs to really master?
Yes,
for science?
Yes, math is a kind of a logic, how to think and how to approach to the solution. So it's a key element in science and engineering.
Well, one of the things that sort of takes a lot of students out of science is that they get into a math course, say an advanced math course, or even a beginning course, and they run into a section where it becomes difficult to understand. It becomes a little abstract for them. What is your advice to them to work around that? Rather than drop the book and leave science, and we lose this potential talent to the world, what do you advise them to work around that so that they can go to the next level? And then use that same technique to deal with the next roadblock that they might encounter.
Well, even in math, there is quite diverse, like geometry and differential equations and so on. So, if you are depending on the individual, you have some preferences, and go further in the detail in the preference area. Like if you like algebra, then study a lot of algebra, and you need to have some understanding of other non-preference areas too. But you can focus in say 1 or 2, 3 areas. Then since it's a learning process and logic process, so in the end, this all meets at a certain point.
In other words, focus on those areas that you know a little bit and get them very strong in your ability, and then, as you say, it meets these other more difficult areas because it's all logical. And then that would make it easier to begin to understand the other areas, because becoming capable in one area strengthens your ability to eventually understand the more difficult areas.
Sure. Yes. So if you are familiar in one area, there can be a catalyst to understand easily in other areas.
That's a very, very good approach, I think. What circumstances in your childhood contributed the most to you reaching your goals in your career? I mean, can you go back and point to certain things that really were key for you?
Well, in 1950s and 60s, Korea was very poor, and most of the people, it's even very difficult to have 3 meals a day. So I think those, I was also went through those periods, and that is also one motivation. Not only the society, environment, and education is a prime motive, and along with those
the circumstances of poverty and hardship were really motivating factors, if you will, to really work hard to get out of that, so to speak.
Yes.
Well, what do you think about the present generation that has more modern conveniences and the lifestyle is good? They in a sense may lose that edge because of that, or are there other circumstances that would benefit them?
Maybe, but one should think of the later part of one's life and what you are going to do in that maybe after 30, after 40, or after 50.
Yes.
So one should think about those projection of oneself in the later part of our life, what you want to be.
Right.
So I think one should be highly motivated.
So they can still be highly motivated because, like for example, youth, for example, in Saudi Arabia, they happen to be in a country that has lots of resources and they are not particularly poverty stricken at all, and so they may not have, say, that kind of strong motivation to get out of poverty, if you will, in order to achieve. So there need to be other factors that they need to consider, as you mentioned, thinking about where will they be later in their life, and what will they be doing? Will it be something interesting? Will it be something challenging, so something that they enjoy? You know, and in that sense, science may be the answer.
Yes, as I have mentioned, it's like a tourist sightseeing.
Yes, yes.
It's a kind of that kind of experience every day. One cannot go to sightseeing more than a month in a year, but if one is doing science and engineering every day, you will encounter new things and should overcome those things.
That's right.
And so on.
So if sightseeing excites you and gives you a lot of thrills, then science is exactly the same or very similar. What would it be, if you will, the highest risks that you encountered growing up to not obtaining your goals? And those risks, how did you overcome those obstacles? You know, you mentioned the challenge of even having all the meals in a day, 3 meals a day. And so, were there other risks involved in that would perhaps hinder you?
Yes, from time to time we are tired. One can be tired about the things one is doing, and one should overcome those. That's the obstacle from the inside is the most difficult.
Internal obstacles. Yeah.
So we should overcome ourselves to reach the goal. And well, in Korea there are so many mountains, so I usually during the weekend went on mountain hiking.
Mountain climbing.
Mountain climbing and hiking, and then it's always it's fun. During the 2-3 hours, you just see the trees.
Sure.
And suddenly at the top you can see all the different mountains and surrounding areas and green fields and so on. So it's always challenging to go up higher and higher understanding. Then we can encounter many different areas.
Right.
So in terms of science or engineering, it's all the as I have mentioned, these roots are all merged at one point. So if you go one deep in one area, then the other roots you can see that easily trace those areas, completely different area from outside. But inside, if you go deep, then they meet at
a similar point.
Physics and chemistry.
Right, right. In other words, nature doesn't have a department of physics and a department of chemistry. It's all one. It's all one, all linked together.
Yes.
But you mentioned that point about hiking. That obviously is a nice balance to, say, sitting down and studying. So the exercise and the ability to go out and think about things, you know, sort of free thinking as you're walking. That's you can be creative and come up with new ideas and so on, I suppose, right?
Yes.
Yeah.
And also playing with others, like soccer, playing team play, and you can learn you can learn not to blame others and so on.
Right.
Things.
So look at it as a group. Yeah. We either rise or fall as a team.
Sure.
And that's a powerful way of looking at it. And that's the advantage of being in that sort of hobby of a team play.
Yes.
Because it carries over to the lab even, because you have to have a good team to accomplish your goals in science.
Yes, it is. Yeah. Teamwork is.
Talk about that a little bit from the point of view of KAUS, because KAUS has a model of interdisciplinary interaction. How do you see that really affecting your potential here?
Well, KAUS is graduate level research university, and so the size is about 250 faculty members, the right size to collaborate in different disciplines, among the different disciplines. So I think there is a big opportunity in KAUS to work with other people within other areas for the synergism.
By having that model, it doesn't have sort of the the history of, say, older universities where they are set up by departments, and these departments are kind of isolated from one another.
Yes.
And here it's an open system in plan and in practice, so that you have a chance to talk to the non-mechanical engineer more easily and find out where you might have something in common that you could collaborate on.
Yes,
right.
yes, indeed.
And that could easily lead to some new breakthroughs potentially.
Sure.
What say areas would be prime targets for you to collaborate with outside of mechanical engineering?
Chemistry, and in combustion we need a lot of chemistry, kinetic data, and also some optics, physics for the diagnostics, and some even in electrical engineering or some plasma assisted combustion area. So even this combustion area itself is diverse, but now it's getting more and more different disciplines to merge together, such as plasma assisted.
When you mentioned physics and optics, I just had a discussion with Professor Boone Oye, who is his specialty is optics, photonics.
Yes.
And he's been very keen on lasers, as a matter of fact. So I'm sure you've had a conversation with him already.
Yeah.
That's right.
As time goes on, now we will work together.
Right. How would you describe your most effective methods for studying and learning? I mean, say you start a new course, and this is going back a ways. And also you talked about after the PhD, you learned chemistry, you learned more physics and so on. What would you do? How would you go about learning a new subject that you didn't know much about?
In old days?
In the old days and even now. I mean, the idea here is what could you give to a student out there who might be listening in terms of an idea on that? Because usually in the school system in most countries, we use the term students being spoon-fed by the teacher. You know, everything comes out of the classroom. But what about that student walking into a library, picking up a book and learning on their own? Now, the student who can do that, and that's actually the key skill that you need in a university, the student who can do that is going to be the most successful student. So what tips do you have or ideas on that?
Yeah, it's if a person finds some his own interesting area, then go deep in that area, and books and nowadays internet is quite powerful, but there are some limitation in the internet, and not that high level of information can be found in internet. So go to the library and dig some books, and then if you are very familiar with one area, then it's easy to expand to other areas. So first focus on the area you are interested in.
Yeah, that's similar to what you said about math, where you run into a situation, focus on those areas that you can do, get good at those, and that's going to give you the tools to get into the areas that you may have difficulty with. I like that concept very much. And also, how important is note taking and being able to write things in your own, I should say, from your own perspective, in terms of trying to confirm your understanding. How do you view that?
Well, it's note. You mean note taking?
Yes.
It's very important. So you hear what the teacher told, and you should digest, and you should write down and summarize during the class, and that is very important to later when you revisit it. It's very important.
As a professor, do you hand out notes to your students, or do you require them to take notes while you're lecturing?
Half and half. If I hand out the material, in most cases students get and then sometimes they get fall asleep, and so It's important to taking notes. Yes.
Right.
Yeah.
Right. So you emphasize that. Any other skills that are important, techniques that you can recommend
Oh, I couldn't think
for
of it.
study? Yeah.
Yes. Oh, revisiting is I think is
Mhm.
you know is after a certain period of time you forget the
Okay.
things. So it's revising and revisiting and
Right.
also reviewing and it's also
Right. In other words, like for example, there's a course that you finished a couple of years ago, and you're in another course that might be related. Go back and revisit that older course,
yes
and go back to some of the basics.
yes
That can help you a lot in your
sure
next level. Yeah, that's another good concept because you'll actually understand that older material a lot better at that point
no sure.
because you've advanced in so many other areas.
Mhm.
Yeah, it all builds. It's a
Yes.
building process, so to
Yes,
speak.
yes.
Yeah, right. Talking about some very good things that students can benefit from, I think.
Mhm.
And one of the things that makes it following up is a part of the process,
Mhm.
to go into depth on things that you mentioned. Okay, what are the most significant breakthroughs in science that you predict over the next 10 years, 25 years, and 50 years? This might take you out of your field a little bit,
Mhm.
but what do you think is going to happen? Your
I think
predictions?
yeah, you just mentioned the prediction, but yes, the predictability is the key breakthrough in the future, I guess, in many scientific areas.
You mean the ability to predict accurately
Yes.
of what might happen?
Yes, this is all, the role of engineer is to predict something
Sure.
from what we know to what we want to know. So this prediction is a prime thing in the next several decades in many engineering and scientific areas.
Why will we be able to predict better? What's going to make that happen?
There is a lot of things that has been unknown in the mechanisms still. For example, in combustion, how the soot particles are formed and how it grows and how it oxidized, and those things are still not well known, and we need to study those detailed mechanisms, and then we build up together and to put it in the computer modeling, and then one can predict the things, what is happening inside the internal combustion engine, for example. So predictability and prediction is the prime breakthrough.
Okay, so now, given that we may have advances in prediction, what do you predict? Okay, we don't have all the math for projecting and prognostication at the moment, but what do you predict, say, in science in general, as will be breakthroughs or big things that will happen in the next 15 years, 25 years, and 50 years?
Yes, it's so diverse in science, and also even more diverse in engineering. So it's difficult to pinpoint one or two things over there. But in overall, as I have mentioned, in many areas of science and engineering, this capability of prediction is, I think, is the. So there is a lot of unknown physics and chemistry at the moment.
Mm-hmm. So you think like advances in the basics of chemistry and physics could lead to breakthroughs in the engineering side? Yeah.
Sure.
Right.
Yes.
Right. No, you don't care to pinpoint any other specific things that you think, something that you dream about that might happen based on the level of science at the moment.
Oh yes, these days biology, nanotechnology, and information technology, those things many people are interested in those areas.
Mm-hmm.
But other than those areas, this combination of these say bioengineering or bio processes and IT and information and nanotechnology and with combined with other areas, there could be a lot of potential in the breakthrough in the future.
So that points out the importance of this interdisciplinary approach at KAUS, because by combining these different fields, there's greater potential for the breakthroughs that the world needs, to solve some of the key problems. That leads me to the next question. What are the most important scientific problems facing the world over the next 15 years, and what would be your proposed methods to solve them?
Wow, that's
another general, broad question.
Yes, there should be a question to Nobel laureate.
You may be the potential next laureate in combustion.
Well, it's different area, people say next in the human society wants live longer and live well, healthier, and so on. So a lot of this things related to the environment. It will be a very important subject in the future.
These are big problems. So, like for example, you mentioned environment. How are we going to solve the environmental problems? What are your ideas on that?
Well, it's different scientists has different approach on the environment. In combustion, it's the pollution and the CO2 problems. But other areas like biology, to understand a lot of biomechanisms and come up with new drugs, medicines, and so on. So there's a lot of different approach in the science advancement for live longer and healthier in the future, I believe.
Are you confident that these breakthroughs will occur?
Well, it will come slowly, and I think we will approach in those targets.
You don't subscribe to the idea of accelerating change, that things will actually happen faster and faster.
Yes.
Is that something you? In other words, things that might have taken, say, 20 years to do in the 20th century, they may take half that time or 1/4 that time in the 21st century.
Yes.
Is that the way the science is changing?
Yes, but it's because of this computers and other things, we could have this acceleration is
the tools.
definitely,
the tools are improving.
Yeah,
so to speak.
Yeah, yes.
Right. Well, can you? You mentioned a couple of the problems and so on. Tie your work specifically to these problems. Like I can understand the role of combustion and then the linking that to the environment. Could you elaborate on that a little bit? How you can tie your work and to the problems that the world face?
Yes. So we have energy and environment problems, and most of the energy is still is converted to mechanical and thermal energy through combustion processes. So in the Clean Combustion Research Center is focused on those to resolve such issues as energy. Keywords are energy, environment, efficiency, and emission in those areas. So that is also crucial for the living standard and atmosphere and the sustainability. So the Clean Combustion Center will work on various aspects to reduce those emissions and to enhance the efficiency. Try to understand more on this, for example, how the suit is formed, the mechanisms, so we could have a predictability in the future, and other for example, how to reduce NOx, what would be the best way to design burners to reduce NOx.
What is NOx?
NOx is nitric oxide. It's coming from the when it's generated from the combustion of fuel. So there are different sources, but nitric oxide, when it comes out, then it could affect the ozone layer and also it can be converted to nitric acid to make acid rain and smokes and those.
So we don't want nitrous oxide to be coming out of the combustion process.
Sure.
Right. So maybe you can demonstrate through maybe talking about a simple experiment that you might perform in your work to explain to, say, a high school student your area of research. Maybe use an example or whatever technique you want to use to sort of explain it. And you already have started that by just saying how it's connected to solving the problem of environment.
Mm-hmm.
But what I'm trying to do now is generate some excitement in a student about what you do. So if you can explain it and then they say, aha, I get the general idea here, maybe I'll try to pursue this area because it's important.
Yes, for example, light a flame. If you light it, then you can see a lot of yellow colors.
Okay.
We call it yellow flame. That color is coming from the black body radiation of soot particles generated inside the flame. And green colors is actually the reaction zone. So, if you have a gas stove, gas oven in your home, then you rarely see any yellow colors. So the flame is quite blue.
And that means that it's burning more efficiently?
It's two different modes. We call it diffusion flame or premix flame. So, and it's all related to the mixing process of fuel and air and the environment and how the fuel and air will be supplied in stages and so on. So there are, it's quite similar to what is happening in the engine. In gasoline engine, we premix fuel and air, and we ignite by electrical spark, and the flame is propagating. And through that, the pressure build up, and they push the piston, so we have a power out of it. And diesel engines, we inside the air we inject diesel fuel with very high pressure, over 1,000 atmospheric pressure, and then it will ignite, and then this burning process will give us power on the system. So from very small things to the large system, like large scale boilers in power plants. The size of boiler is in many cases over 70 meters tall. So it's a very large size system. And we should understand those large scale phenomena too in the board.
What would that be involving? Heating a campus like this, or heating a factory, using energy for a factory? That's when you would have a large system like that?
Power plant.
Power plant.
Yes, from this boiler, you heat up water to make it steam, high pressure, high temperature steam, and the steam goes through the steam turbine, and turbine turns the generator and generate electricity.
Oh, electrical generation.
Yes.
Oh, yeah, right. So, here's a question about the internal combustion engine. This was originally developed in the 1800s, 19th century.
Yes.
Why hasn't there been a fundamental major transformation of that technology over all these 100 and plus years? Why has it more or less stayed pretty close to the same technology? Well, obviously with a lot of improvements, but
yes.
the basic technology is the same. You would have thought, like in, say, in electronics, we we went from the vacuum tube to the transistor and to the semiconductors and so on. That kind of process was really major shifts. But that didn't happen in the automobile industry. Why not?
Well, the principle is the same as compared to 100 years ago, but there is a lot of improvement, a lot of controls go into the system. High pressure and efficiency goes up significantly. Well, why in the modern times we have only 4 power generation system that we can operate at our will. Those are 2 reciprocating machine like gasoline and diesel engines, and 2 rotating machinery. One is gas turbine and the other is steam turbine. And there are other things, but those 4 are most economical system to generate power. So in engineering, always we should deal with the economy. How economic the system is.
Right.
So far we could not find another system
that could replace it.
They can replace it. People are working on fuel cells, but it's very, very expensive. For example, if one doesn't want to put the fuel cell system, spending $100,000 for a car.
Right.
So economy is always linked to engineering application, and I think so far in the human history that's the 4 system. Yes, there are other systems, so wind turbine and solar and so on, but we cannot operate those things at our will, because if sun goes down, we cannot use solar cells.
And the wind stops.
When the wind stops, we cannot do it. But in many cases, those, especially for electrical energy, it cannot be stored effectively. So we should, demand and supply should exactly match.
That's what I was going to ask you. The next question is, well, we see a big shift now in many manufacturing concerns toward the hybrids, as well as the total electrical car. Do you see a bright future in that shift?
We should work on that, but it will be quite slow, I predict, because, for example, now we are in developed countries using electricity about 25%, and transportation is also 25%, which means if we convert all the transportation with the electric system, then we should build the equal amount of power plants.
There's not enough to generate all the electricity to convert all the transportation.
No.
So, okay, that's 50%. What about the other 50%? That 25, what is the other 50%?
No, some industries and households.
Oh, okay,
Yes.
okay, yeah, different other usage of the energy.
Yes.
Okay, moving right along, we're getting toward the end here. I don't want to take up too much of your time from the office. What research breakthrough do you anticipate in your line of work, and what would it mean for Saudi Arabia and the world?
As I have mentioned, kept on mentioning, the energy and environment is highly tied in combustion area. So detailed understanding of the combustion phenomena, some mechanism development, and understanding of physics all could be a major breakthrough, and that will benefit the kingdom. For example, how to formulate, say, fuel. And fuel composition is very much varying. There are many, over 100 different kind of composition. And how to blend those fuels to best fit the gasoline engine or future engines, future internal combustion engines that is currently developing, such as it's called HCCI, PCCI concept of controlled auto ignition engines, low temperature ignition engines, low temperature combustion engines, and those will benefit the kingdom for those fuel combinations.
Is there any connection in what you do and the potential for carbon sequestration?
Oh yes, carbon sequestration, we need a high concentration of CO2 emission from combustion. Carbon sequestration is the prime target is for the stationary sources like power plants.
Power plants, right.
And then if we use air, then there are a lot of nitrogen, more than close to 80%, 79% of nitrogen and 21% of oxygen. And after combustion, it generates CO2 and H2O. And if you try to sequestrate the CO2, there are too much amount of nitrogen over there. So in terms of a combustion, we studying oxy-fuel combustion. Instead of using air, we first separate the nitrogen and oxygen in air and use that only oxygen and to burn fuel. Then theoretically, you can, since there's no nitrogen,
to block the sequestration.
And nitric oxide is
would be the byproduct when that's present. Right, you would avoid that.
And then we have a high concentration of basically in the exhaust we have carbon dioxide and water vapor. If we condense the water vapor, then it's a very maybe purely CO2. Then if we compress that, then it's ready to sequestrate.
Right. So those are all potential breakthroughs that might occur. How long do you think this will happen? You know, we're going to put on your prediction hat again. In 5 years, 10 years?
Well, it will take some time. It's, I think maybe 10 to 20 years. As I have mentioned, there is always economy is coming in engineering areas.
Right.
So now they are testing those possibilities, like a future gen program in US. But this the dissemination of those technology to the society might take some longer time.
Yeah, because I mean that's obviously a very important point, because even if we have a breakthrough tomorrow in, say, combustion, you have all of this established infrastructure that's using the old technology.
Yes.
How do you convert it? I guess one of the big breakthroughs would be a way in which you can convert what's presently existing to something new.
Sure.
Yeah, and keep that old infrastructure. Because can you imagine all the cars on the road today? We have to come up with new cars with the new technology. That's will, as you say, take time.
Yes.
Yeah.
For example, is right now we have a petrol station in the world.
Yeah, right.
Once we change the say fuel cell vehicle, they use hydrogen.
That's right.
Well, we should install this hydrogen fuel station
all over the world.
All over the world, and it takes a lot of money.
Yeah, exactly.
So it will be changing slowly to that process.
A gradual shift. Yeah. What advice would you give to those who might want to pursue exactly what you do?
Well, this combustion is a very diverse area. It requires a lot of different disciplines and combined together in one area. And among the mechanical engineering or even chemical engineering is one of the most diverse area in the field. So it's fun, and then also you can contribute generation of power. One can contribute reduction of emissions, and so one can contribute to environment and energy problems. So there's a lot of.
How many people in the world would be doing this at the moment? Say, what is it? What are your ranks? Of clean combustion specialists around the globe. What would you estimate is the number of researchers doing this?
Oh, there are several societies like the Combustion Institute, and there are also many societies on internal combustion engines and power engineering side, and also gas turbine.
So we say tens of thousands?
Tens of thousands.
Oh, that many, large number.
Yeah, and there are many engineers working on those areas.
So it's not that there's a shortage of personnel particularly. There's quite a bit of people doing this now.
Yeah, quite a people doing, but some competent people we always need it.
Right. So it's always good to get new blood, so to speak, coming in, new ideas, new ways of thinking.
Sure.
Right. So you think chemical engineering and mechanical engineering would be key disciplines to have a background in to go into your area?
Mechanical engineering and chemistry.
In chemistry,
Yes.
more so than chemical engineering.
More than chemical.
So chemistry,
yeah.
Per se, yeah.
But one could not get all kind of those disciplines. So one good mechanical engineer can absorb the chemistry.
That's right.
And chemistry people absorb
the chemical in a few
mechanical.
courses or
Yes.
right. And then that shows the importance of teamwork, because on the team you're going to have both of those,
Sure.
and maybe
Yes.
some other specialists as well.
Yeah.
We stand on the shoulders of giants in science. That is, whatever we are doing is based on what pioneers have done before us. Who would be the pioneer researchers in your field, and what was the breakthrough that they accomplished?
Well, it's starting. The combustion history is they say started 500,000 years ago, but it's too far back in the history. And recently, there are some names like Jeldovich and from Raman and other.
Where are they from? From Germany or Europe? Or
Russia.
Russia.
Jeldovich,
Uh-huh.
Russia.
And what did he do?
Expanding our understanding of flame structures.
This is how recent is that?
So he passed away only several years ago.
Oh, just not very long
In
ago.
the 40s.
Oh, okay. And any other big names that you sort of looked up to?
In old days, Bunsen flame, like Bunsen or something.
The Bunsen burner?
Yeah, Bunsen.
Yeah, from the classic lab.
The lab is
yeah.
Bunsen. And, many names that is related to chemistry. It's worked on combustion.
Yeah. Who would you say is the inventor of the internal combustion engine?
Inventor. Well, it's called autocycle, so auto.
Is it like one person or a group of people, or?
Well, it's evolved a little bit, and suddenly it's coming into market.
So it was I look at the classic automobile companies like Ford and General Motors and then Mercedes, Benz. Okay, they took this technology, but obviously just before that, something preceded that. Was it modeled after some of the large stationary systems?
Yeah, we had this James Watt.
James Watt.
Yes, that's the external combustion engine.
Right.
Steam engine.
The steam engine, right.
Yes, but it's obsolete now.
Sure.
But we had this reciprocating motions.
Right.
And that can be
precursors.
Precursors.
Right.
And using directly this combustion power to generate combustion process to generate power. Gasoline engine and diesel engines.
What would you say is the greatest achievement that you've made so far in your profession? I noticed on your CV you've gotten in quite a large number of awards and honors. You were an American Society of Mechanical Engineers Fellow in 2007. You're a National Academy of Engineering of Korea candidate member. Korean Academy of Science and Technology Fellow. What would you say? You achieve these awards. That's based on what do you look at as your top achievements so far?
Mm-hmm.
Maybe 2 or 3 things.
Yes, one is that, as I have mentioned previously, there are 2 different types of flames. One is diffusion flame, and the other is premixed flame. Premixed flame is fuel and air is well premixed, and diffusion flame is fuel and air are separated by reaction zone. And there are the new type of flame is we call the partially premixed flame. And I have worked by some time on those characteristics of this partially premixed flame. So in between diffusion flame and premixed flame type of thing. So that is becomes quite important in various flame stabilization.
Has it become widespread in use now, or
yeah, in modeling it's important as well these days.
I noticed that you have quite a large number of international journal publications. How do you account for that? I mean, the steady work in your lab. When you produce a certain amount of data, what is that process? You produce a certain amount of data. You start analyzing this data, and then you decide that this is worth a publication. How does that
Yes.
process work?
Well, in the engineering publication, if you observe a new phenomena, that is could be a good paper, and also as it comes back to prediction. If you do a research, it's for predictive purpose. Later, some people does not need to repeat those experiments. So for prediction, one can come up with some generalization of the phenomenon. So one needs to generalize the phenomena, or at least the parameter dependence. So if we can come up with those things, then we decide to publish.
So you view that as a great potential here, that you can generate a lot of new things, so to speak. That would be worthy of publication over here in Kaus.
Sure.
Coming down to the last 3 questions here, what are your future goals in science in your field?
Well, it's always if you. I'm still young, but as getting older, you want to see to educate young blood and for them to become successful. So it's the next goal is so far I tried my best for the success of myself, but I will spend more time on for the success of the young people. So
in other words, you want to convey your knowledge and experience to the next generation.
Next generation,
right.
New PhD, new. So far I did, but here there is more collaborative environment, so I will pursue that.
And people from more countries.
Sure.
And I was curious. I mean, you obviously had that great experience of building your lab, building your team there. Here, you're a director of a major center at Kaus, one of the 9 centers that will be starting out at Kaus. Obviously, that gives you some sense of a challenge, and also, to be able to build another center. You can use all of the experience you had building your first center to build another big center of clean combustion research. How does that? What is your comments about that?
Well, it's a challenge, and there's an opportunity. So I think it will be very fun in the future, to see the growth and to work together. And
How many people you have on your team already?
We started very late among the 9 centers,
Right.
so it's quite a limited number, but within several months the number will be growing to 10s and 20s.
Right. Describe a typical working day in your profession, from the time you get to your office and to the time you leave. What happens? What do you do?
Well, discuss with my students about their progress.
These are your PhD students and master students?
Master and PhD students.
How many do you typically have, say in your previous position, how many would you typically have?
About 10.
10 in a given year?
In a given year. And we discuss the things and how to improve the results and those kind of discussion. And
That's the first thing in the morning, you have a meeting with the team.
Yes, not every day, but
Yeah.
I should give them some day
Sure.
to prepare those things. And reading papers and writing papers. Writing papers is also, as I mentioned, documentation
Right.
process.
Documentation, yeah, you go back to, that's really good advice for
Yes.
a young scientist to.
And not only that, writing the essence, but how to convey those things to others is very important. So to write the things in the perspective of a reader rather than a writer perspective.
So your audience.
Yeah, audience
Mhm.
perspective. Yeah.
So you'd have your students practice presenting to your team
Yeah,
and you would be the audience for them.
Yes,
Yeah.
it used to be every week we had a meeting and presenting what the students have done, and we give some advice to them how to.
So those meetings that you mentioned in the beginning of the day, or on one of those days when you have a meeting, you would have each student go through what they did in front of the others, and then you would sort of make suggestions to them of how they can go forward and do more and improve and so on.
Sure.
On a daily basis. But so you wouldn't have one-on-one sessions with students on that, or is it mostly always a group session?
Oh, it depends. We have a group meeting, and after that, if there is a need for one-on-one session, then we also do
Right.
that.
So what else happened in your typical day?
Well, it's there's a lot of communication, a lot of meetings, and also the
Like when you say communicate, you mean emails, that sort of thing, or
email or the discussion with others
Mhm.
and some other
brief meetings here and
Yes,
there and so on?
yes.
Would there be a track of time you always set aside where you're working without being disturbed?
Well, nighttime is the good time for not to be disturbed.
Well, that goes to the question of how long is your typical day? I mean, that you actually working? Well, how many hours? would you say?
Well, it depends on that day. Yeah.
Would it be past, say, 10 hours?
Yeah.
12 hours like
About
that?
10, 12 hours. Yeah.
So you're in the office, you do the work there, you get there about 8 o'clock, I imagine, and what time do you leave?
Well, it depends on leaving is not much meaning because one can walk at home.
That's right, so that's what I mean. I mean, you leave and you go home and you maybe have time for, dinner and family, and then you start working again for a few hours in the night.
Yeah, many days, yes.
Yeah, until
But
then.
not always.
Not always, yeah, but I mean, occasionally, it depends on what's happening.
Sure.
And that could go to what, late into the night?
Yes.
Yeah, if necessary.
Yeah.
Right. So you're very inclined to pursue this, whatever, if there's something that really needs pursuing, you put the time in for that.
Mm-hmm.
So your long day could be 15 or 16 hours, right? I mean,
It could be, but I'm not a workaholic.
Yeah, right.
But we need some ideas, fresh ideas.
Right.
So we need some time to rest.
Sure.
Yeah, but during the rest, one also have some thinking processes.
The subconscious is
Yeah.
kicking in
Yeah,
with continuing Well, with the problem solving. Now, what about your hobbies? So you mentioned that you need some time. What do you do that's completely different from clean combustion as a hobby, as hobbies?
Oh yes, I had a hobby of mountain climbing, and when I was there in Korea, because we can reach within 1 hour many different mountains, and so.
Mm-hmm.
The other is the taking photographies.
What about how many children do you have?
I have one.
One child. And so obviously that was something that you had to devote time with. They would go mountain climbing with you, right?
Oh, she's studying in US. And all grown up now.
Oh, okay. So which university is she studying in US?
Wisconsin.
Wisconsin, University of Wisconsin, Madison.
Yes.
Madison. Fantastic. Okay, last question. What is your definition of success?
Self-satisfaction, maybe. Success is it should be measured by internally. So how much you are satisfied in your life is the measure of success.
Okay, that's quite a measure. I mean, in other words, you don't necessarily depend on whether someone else is considering you successful.
No,
it's an internal.
Sure.
It's an internal compass about what you have done.
Mm-hmm.
Yeah.
Well, everyone has come from different circumstances, and circumstances influence a lot of one's life. So how much you are satisfying yourself is, I think, is the measure of success.
Professor Suk-Ho Chung, thank you very much for a wonderful interview.
Yeah, thank you.
I apologize for taking so much of your time, but I think you have provided valuable information for our young scientists
Thank you.
out there.
Yeah, my pleasure.